All right, so now we are going to continue our notes from yesterday over the properties of logs. All right, so we're going to learn about the change of base formula. Logs with any base other than 10 or e can be written in terms of common or natural logs using the change of base formula. This allows you to evaluate any log using a calculator. Okay, so I've got log base c of a equals log base c of a over log base b of c. Okay, so log base c of a equals log over a over log of c. So an example with that one would be log base 2 of 6. I can rewrite that as log of 6 over log of 2. So log of my value over the log of my base. So we're going to do that over here. So for a here, I will have my log of my value, which is 8, over the log of my base, which is 5. Okay? So that is equivalent to 1.292. And I'm going to do the same thing for b and c. My log of my value over the log of my base. So log of 14 over log of 8. And then we just put that right into our calculator to get 1.269. All right, then I go over to this last one, and I've got log of my value over the log of my base. And we put that right into our calculator, and we should get 0.674. All right, so for a sound with intensity I in watts per square meter, the loudness, L of I, of this sound in decibels is given by this function, where I sub 0 is the intensity of a barely audible sound, about 10 to the negative 12 watts per square meter, and we want to find the decibel level of the sound made by each of these objects. So I want to find the loudness of a barking dog, which is 10 to the negative 4th. So I'm going to plug that right into this formula. So I've got my L of I equals 10 times my log of I over I sub 0, and then I'm going to plug that right in. So L of 10 to the negative 10 to the negative 4 equals 10 times my log of 10 to the negative 4 over 10 to the negative 12. And I know that it's 10 to the negative 12 because up there it states that my I sub 0 is 10 to the negative 12. All right, so to simplify this fraction here, I can just subtract the exponents, right? So I've got negative 4 minus negative 12. So that'll leave me with 10 to the positive 8. So I've got 10 times my log of 10 to the positive 8. All right, so now I want to use what we learned yesterday about the power of logs, how I can take the exponent and pull it down at front. So that's what I'm going to do. I've got 10 times 8 times my log of 10. All right, and I can rewrite that as 10 times 8. And that'll give me 80 decibels. And I can rewrite that as 10 times 8 because if over here I see that my common log has base 10, so I'm going to set my log base 10 of 10 equal to x. And then I'm going to do my log ride, and I'll see that 10 to the x equals 10, so x equals 1. So that just means that this whole thing here is equivalent to 1. So that's why I could just multiply all this down here by 1. Okay? This second one, we're finding the loudness of an ambulance. So I'm plugging in 10 sub 0 into my formula now. All right, so once I simplify my 10 to the 0 over 10 to the negative 12, that's the same thing as writing 10 to the negative 12 because 10 to the 0 power is 1. Remember, anything to the 0 power is 1? All right. So now I bring my exponent out front, and I've got 10 times 12 times log of 10 equals 10 times 12 times 1 basically, so that's just 120 decibels. Okay. Now I'm finding the loudness of a bee, where I equals 10 to the negative 6.5. So I'm going to plug that right into my formula. Okay, and then I'm going to simplify this 10 to the negative 6.5 over 10 to the negative 12. And I've got 10 times my log of 10 to the 5.5. And I'm going to do the same thing. I'm going to pull my power out front. So that leaves me with 10 times 5.5 times log of 10, which we already said was 1, so we know it's just 10 times 5.5, which is 55 decibels. All right, the next page. If b is a positive real number other than 1, then b to the x equals b to the y if and only if x equals y. So for an example, if 3 to the x equals 3 to the 5th, then I know that x equals 5. Okay, so using method number 1, we're going to solve exponential and log functions. Use the property of equality for an exponential or log function. If the bases are the same, then the exponents are equal. So, for example, we're going to work on this one, this 9 to the 2x equals 27 to the x plus 1. So our first step is to find a common base that can be raised to different powers to equal the bases in the original problem. So I know that 9 can be rewritten as 3 squared, and 27 can be rewritten as 3 to the 3rd. So I'm going to rewrite those numbers. All right. So now I see that I have the same base. So my next step is going to be distribute those exponents. So I take 2 times 2x and 3 times x minus 1. So I've got 3 to the power of 4x equals 3 to the power of 3x minus 3. And my next step, since I've got the bases the same, I'm just going to set the powers equal to each other. So now I have 4x equals 3x minus 3. All right, now I'm trying to solve for x. So I'm going to subtract 3 on both sides. So I see now that I have x equals negative 3. All right, now let's do some more practice. I want to set my bases equal to the same thing. So I want to get my bases to be the same number. So over here, I know that 5 to the x minus 4 power is the same thing as 5 squared raised to the x minus 6. And then I can simplify that down by distributing my exponents. So now that my bases are the same, I can set both of them equal to each other, both my exponents equal to each other, and then solve for x. Okay, and once I do that, I solve for x, I'll see that I found 8 equals x. All right, this second one, we're doing the same thing. I know that I can simplify down that 81. I know that 3 to the 4th power is also the same thing as 81. So I'm just going to rewrite that as 3 to the 4th power to 12 minus 3x. And then I want to distribute that exponent. All right, and now that I have that, I have the same base, so I want to set my exponents equal to each other. That's my next step. And then after I set them equal to each other, I'm trying to solve for x. So I want to add 12x to both sides, and I want to add 7 to both sides. So that leaves me with 15x equals 55. Now when I solve for x, I see that x equals 55 over 15. But I can also simplify that down to be 11 over 3. And that's my answer. All right, this last one, C. I know that I need to get 36 the same base as my 1/6. So I need to get 36 to be equal to 1/6. And I know that if I take 6 squared, I'll get 36. So if I take 6 to the negative 2nd power, that'll give me 1 over 36. So if I take 1/6 and raise it to the negative 2nd power, I should get 36. And then I've still got my 5x plus 2 as my exponent, and I set that equal to 1/6 to the 11 minus x. So now I need to distribute my exponent. All right, and now that I have the same bases, I can set my exponents equal to each other. All right, now I'm solving for x. So I've got negative 4 equals 11 plus 9x. And I'm going to subtract 11 from both sides. So I've got negative 15 equals 9x. And that'll give me x equals negative 15 over 9. And if I wanted to check that, I could plug that number back in to my top equation here. Okay? All right, so now we're solving for extraneous solutions. Because the domain of a logarithmic function generally does not include all real numbers, we have to be sure to check for extraneous solutions of log equations. So that just means a solution that we get that, when we plug it back into our equation, would not work. Okay? So we can do this algebraically or graphically. So I need to solve this problem. Log base 5 of 4x minus 7 equals log base 5 of x plus 5. I need to solve for x. Okay, so I notice that the bases are the same. I've got log base 5 on both of these. So I can just cancel those logs out basically, and I've got 4x minus 7 equals x plus 5. And I'm going to solve for x. So now I've got 3x minus 7 equals 5. And when I add 7 to both sides, I'm left with 3x equals 12. And I solve for x, I find that x equals 4. All right, but now I have to check that answer. I have to plug that back into my original equation. So I know in order for this to be a solution, it cannot have a negative inside my log. So if I plug 4 in and I get a negative number for my value, it would not be an answer. It would not work. But when I plug 4 in, I've got log base 5 of 4 times 4 minus 7 equals log base 5 of 9. And then I plug it into my other side, equals log base 5 of 9. So that checks out. That works. All right. So checking this graphically, if you pause here and put both of these into your graphing calculator, so you'll go to y equals, and then you'll type in log base 5 of 4x minus 7 into one line, and then in the next line you'll put log base 5 of x plus 5, and then you'll hit table, second table, so second graph, which will bring you to your table. And we want to look at when x equals 4. We need to make sure that those numbers are equal to each other. So when x equals 4, my y values have to be equal to each other in order for this to be an answer to my solution. Okay? And if yes, then it's a solution. And if not, then it would not work as a solution. All right. So the second method is changing forms. So if it's exponential, we want to rewrite it in log form. And if it's in log, we want to rewrite it in exponential form. And we have lots of practice of doing that. So I'm going to go on my log right here, and I've got log base 4 of 11 equals x. And then I plug that into my calculator, and I'll find that x is equivalent to 1.730. And I'm going to do the same thing with all of these. So all I'm doing is solving for x for all of these. Okay? This next one, I'm going to rewrite it in exponential form and then solve for x. So I'm going to get x by itself. And for the third one, I'll find that x equals 13. All right, and the log right again, I get 2 to the 5th equals the entire value, which is x minus 6. And then I'm solving for x. And I'll get 38 equals x. All right, so we're using the log properties that we learned yesterday to help us solve logarithmic expressions. So my first step here is to notice that I've got 2 logs with the same base. So I can take those and rewrite them as log base 2 and then multiply the values inside. So I've got log base 2 of x squared minus 2x equals 3. Okay, and now I need to change forms to solve for x. So I'm going to do my log ride. And then I'm left with x squared minus 2x minus 8. Okay, so I need to find something that adds to negative 2 and multiplies to negative 8. And I found that was negative 4 and positive 2. Then I'm going to set those equal to 0, and I'll have two x values as my solution. But I have to check those, so I've got to plug them all back in. Or I can plug them into my calculator and see. Okay, so I found when I plug in 4, I get log base 2 of 4 plus log base 2 of 2. But when I plug in negative 2, I have negative values. And I can't have negative values. So that means negative 2 is not an answer, but x equals 4 is a solution. All right, so I'm going to do the same thing over here. My first step is going to be to get the natural log by itself, so I want to subtract 3 from both sides. Then I'm left with 4 times the natural log of negative x equals 18. So now I want to divide by 4. Instead of moving it to the exponent like I would typically do, I want to divide by 4 because I'm trying to get x by itself. So then I'm left with the natural log of negative x equals 9/2. And now we're going to go on our log ride. So I've got e to the 9/2 equals negative x, or x equals negative 90. All right, and I've got to plug it back in to check. So I get 4 times the natural log of 90, which is 21. And that's okay because I have a positive number inside of my natural log. All right, this last one, I have 2 logs being added together, so I can go ahead and multiply those values. And then I'm going to distribute. Some people do the box. I use the FOIL method, so whichever method you like here, you can use. All right, so now I want to change forms. I want to go to my exponential form in order to solve for x. Okay, and I want to make sure everything is on the same side of the equal sign. So I've got x squared minus 12x plus 18. All right, and now I need to plug it into the quadratic formula, if you remember. So I need to solve for x, and a way to do that is to plug it into the quadratic formula. All right, so once I do that, I get down to 12 plus or minus 6 square roots of 2 all over 2. And that simplifies down to 6 plus or minus 3 square root of 2. And that, once I plug it into my calculator, I'll get 10.24 or 1.76. Now I need to plug both of those numbers in to my original function up here to check them. And when I did that, I found that I have a negative inside my value here if I plug in 1.76, and I don't whenever I have 10.24. So I know that 10.24 is my answer. Okay, Newton's law of cooling. An important application of exponential equations is Newton's law of cooling. This law states that for a cooling substance with initial temperature T sub 0, the temperature T after little t minutes can be modeled by T equals T sub 0 minus T sub r times e to the negative r little t plus T sub r, where T sub r is the surrounding temperature and r is the substance's cooling rate. So we're going to use that to solve these problems. So I'm cooking a licha, an Ethiopian stew, and when I take it off a stove, its temperature is 212 degrees Fahrenheit. The room's temperature is 70 degrees Fahrenheit, and the cooling rate of the stew is 0.046. I'm trying to find out how long it'll take to cool the stew to a serving temperature of 100 degrees Fahrenheit. So first I'm going to identify all of my variables here, and then I'm going to use them and plug them right into my equation, right into that formula I was given. Okay, so now I'm trying to solve for t. So my first step is going to be to get rid of this 70 here. So I need to subtract 70 on both sides. All right, now I'm going to divide by 142 because I want to get e alone on one side. And then when I get to here, I need to change form. So I need to go into log form. But since I know I have an e here, it's going to be the natural log. So I've got the natural log of 30 over 142 equals negative 0.046 t. And now I'm solving for t. So I've got t equals 34 once I plug all of that into my calculator. So 34 minutes. All right. A car overheats at 280 degrees Fahrenheit and can be driven again at 230 degrees. If R is 0.0048 and it is 80 degrees Fahrenheit outside, how long in minutes do I have to wait until I can continue driving? So my first step is to identify all my variables, and then I'm going to plug them right into my formula. Okay, and then I'm going to solve for t here. So I want to get e by itself. So I need to subtract 80 from both sides. Okay, and then I'm going to divide by 200 on both sides. So I get 0.75 equals e to the negative 0.0048 times t. And here's where I need to change forms. So I need to change this to the natural log. So the natural log of 0.75 equals negative 0.0048 t. And we're trying to get t by itself. So I've got the natural log of 0.75 over negative 0.0048 will be my t. So I'm going to plug that whole thing into my calculator, and I should get t equals 60 minutes. So I have to wait 60 minutes until I can continue driving, an entire hour. Okay. The last one. Just out of the oven, beef stew has a temperature of 200 degrees Fahrenheit. The room temperature is 75 degrees Fahrenheit, and the cooling rate of the beef stew is R equals 0.054. How long in minutes will it take to cool the beef stew to a serving temperature of 100 degrees Fahrenheit? So again, my first step is to identify my variables. All right, and then I'm going to plug them right into my formula. So go ahead and solve this on your own, and then we'll pause the video, solve it on your own, and then once you've solved it, press play and find out if we got the same answers. Okay, so you should have gotten, the time is about 30 minutes. All right, and this concludes the notes for concept 27 and 28.